We can use the property of logarithms to solve logarithmic equations. And in this video I'd like to look at some examples that use method 1, where the equation can be written in the form log base b of some expression, f of x, equals c, equals some constant number. And in that case we can then rewrite it as an exponential equation, and the variable will not be in the exponent because c is constant, and we can solve it from there. So in the first example it's very straightforward. We're kind of all set up to do that. The base is 2, so the equation can be rewritten as 2 to the third power equals x minus 5. Because if you think about what this logarithmic equation says, it says 3 is the exponent, that if I raise 2 to that power, I get the argument, x minus 5. So to finish solving the equation, we can rewrite 2 cubed as 8, 2 times 2 times 2, and then add 5. And we see that the value of x should be 13. Now, it's important to remember for these logarithmic equations that we should check our work, check our solutions in the original equation. Because in addition to just catching arithmetic mistakes, it's possible that we might create a solution that doesn't actually solve the original equation. In this case, we're okay, right? If we plug that back into the original equation, we end up with log base 2 of 13 minus 5, and the exponent that I need to raise 2 to get 8 is 3. And so it works. Log base 2 of 8 is equal to 3. Now with this second example, things are a little bit more complicated. We're still going to use method 1 because we do have a constant on one side of the equation, but now we have 2 logarithmic expressions on the other side. Because there's a plus sign in between them, I want to use the product rule to combine those into a single logarithm. And then after we do that, we can solve it the way that we did the first example. So let's look back up at the product rule here. What we have is something that looks like the right-hand side of the product rule. So I want to translate that back into the left-hand side. So for this example, we can rewrite the left-hand side as log base 4 of the product x minus 4 times x minus 10. And so it might be nice to multiply that out before we continue. And so this can be thought of, this is log base 4. We're just doing some algebra here inside the logarithm. We get x squared minus 14x plus 40. And now we can apply our method. Now we can apply method 1. And this argument is going to come outside if I rewrite it as an exponential equation. So the argument comes outside, and then I get the base raised to this exponent. So then on the other side I get 4 squared. And now we can subtract 16 from both sides, since 4 squared is 16, and solve the quadratic equation x squared minus 14x plus 24 equals 0. And it turns out this factors, so it's not a terribly scary equation to solve. It factors as x minus 12 times x minus 2. So the two solutions are x equals 12 and x equals 2. And I should say the two possible solutions are x equals 12 and x equals 2. If x equals 12, then the original equation becomes log base 4 of 12 minus 4 is 8, so log base 4 of 8, plus log base 4 of 2. And we can make sense of both of those numbers because the argument inside the logarithm, for both of these logarithms, the argument is positive. And to simplify it, we could multiply them together. So we get log base 4 of 8 times 2 is 16, and the exponent that I need to raise 4 to in order to get 16 is 2. So it checks out. So 12 is an actual solution. If x equals 2, however, we end up with log base 4 of negative 2 plus log base 4 of negative 8. And so after applying the product rule, negative 8 and negative 12 is positive 16, but this original statement makes no sense. Right? These are not numbers. I can't evaluate a logarithm for a negative number. And so 2 is actually not a solution. And so the only actual solution to the equation is x equals 12. So it is really important for logarithmic equations to make sure that we check the solutions, because there could be, in the process of combining logarithmic expressions especially, we could create extraneous solutions that don't actually solve the original equation.